Consider this set consisting of all the points on the line in between the two parentheses. We can say that this set is connected because it has no gaps between points. Now, removing a point in the middle of the set creates a hole that makes our set not connected. Similarly, if we add a point far enough away from the set, it makes our set not connected. With this example, we have seen two things. Removing points from a set does not preserve connectedness. And adding points to a set does not preserve connectedness. However, there is a certain type of point that we can add that will preserve connectedness. A limit point of a set S is a point that is infinitely close to S. It turns out that adding a limit point to a set keeps it connected. We'll take a look at an open disk. That is, a circle missing its outer edge. You can see that any point in the border of the circle is infinitely close to the inner portion of the circle. Thus, we can add the border to the disk and keep it connected. Another notion of connectedness is what we call path connectedness. A space is path connected if given any 2 points in the space, there is a path between the points. This path does not have to be a straight line. The only requirement is that it is a continuous path with no breaks. Additionally, the path may not leave the space. These two circles are not path connected because there is no path joining points in different circles. Shockingly, path connectedness is not the same as connectedness. Here is a famous example of a space that is connected but not path connected. We will draw the function sine of 1 over x on the open interval 0 to 1. You can think of this function as taking the normal graph of sine and squeezing all of its infinite oscillations into the interval 0 to 1. Notice how the graph oscillates an infinite number of times as our x value approaches 0. This graph is clearly connected because it can be stretched out into a line, which is connected. Now we will add all the points on this vertical green strip. Observe that any point on this green strip is a limit point to the graph. Thus, the combination of the yellow and green is a connected set. But we claim that this set is not path connected. We will select 1 point on the green strip and 1 point on the yellow graph. As we try to find a path between these 2 points, we will move the right point along the graph to get closer to the left point. As we continue to travel, the point gets closer to the left point while oscillating more and more. Due to the oscillations, this point will get infinitely close to the other point, but will never reach it. This space is called the topologous sine curve, and it is an important example of a space that is connected but not path connected.